Alright, hopefully everything went well yesterday with the quadratic formula and completing the square. Today we're going to talk about solving equations that go beyond quadratics, such as cubics and fourth roots. And then we're also going to talk about what if I tell you the roots, can you write the equation? I'm going to actually teach you two methods for this, but let's start with the solving. So if we're solving a cubic equation, what you should be recognizing about this problem is that I could rewrite it as x to the third minus 5 to the third. And earlier in the year we talked about how to factor a difference of two cubes. We're going to break it down to x minus 5 times x squared plus 5x plus 5 squared, which is 25. So the easy part of this is to just go ahead and set x minus 5 equal to 0. So we get x equals 5. The more difficult part is the quadratic equation that we're left with. Remember I told you back when we were factoring that this part is never going to be factorable more. So you don't even really have to bother trying. But if I want you to solve that, then we have to use either the quadratic formula or completing the square. I'll go ahead and use the quadratic formula. So if I do that, x equals negative 5 plus or minus the square root of 5 squared minus 4 times 1 times 25 all over 2 times 1. So we get negative 5 plus or minus the square root of 25 minus 100 over 2. 25 minus 100 is negative 75. We can break that down to 25 times 2, times 3, So we're looking at negative 5 plus or minus 5i root 3 all over 2 as our other two answers. Notice that when we solved an x cubed, we ended up with 3 total answers. X equals 5, and this one is representing 2 answers, negative 5 plus 5i root 3 over 2, negative 5 minus 5i root 3 over 2. Alright, we're going to do something similar with the x to the fourth problem. We're going to start by putting everything on one side so that we can factor. 16x to the fourth minus 625 equals 0. 16 and 625 are both perfect squares. So I'm going to do perfect square factoring, my favorite. So this would be 4x squared minus 25 and 4x squared plus 25. Then I can set each of those equal to 0 and just solve with the square root method. So if 4x squared minus 25 equals 0, I add the 25 over to the other side, divide by 4. X squared is 25 over 4. Then I'll square root that. Those are both perfect squares, so I get x is plus or minus 5 over 2. And then when I set the second equation equal to 0, I'm getting almost the same thing, except that the 25 when I move it over is negative. So x squared is negative 25 over 4. So this time I'm going to have an I in my answer. X is plus or minus 5i over 2. Again, notice that it's degree 4 in the original problem, and I ended up with 4 answers. Okay, next let's talking about working backwards. What happens if I tell you the roots for an equation, and then I ask you to write an equation with integral coefficients of least degree? Well, keep in mind that these roots are what you get once you've set your parentheses equal to 0. So if I'm going to get an answer of negative 2 when I'm solving, the parentheses need to start with the opposite sign. So it would start with x plus 2 and minus 8. Think about if you were to keep solving here, you would get x equals negative 2 and x equals 8 for your two answers. So this is the first step, is just to turn the roots into factors. And then for your final answer, they want you to actually FOIL this out. So we've got x squared minus 8x plus 2x minus 16. Combine like terms. So we get x squared minus 6x minus 16 equals 0. Okay, let's also talk about this word integral for just a minute. Integral means no fractions in your answers. It means we're going to have integers as our coefficients. that's going to come into play a little bit later today. Alright, so the next one again, we're going to start by turning the roots into factors. When you do that, you're basically just giving the factor the opposite sign of the root, and then again, foiling so that you can get your final answer, x squared plus 9x plus 20 equals 0. Now, this method of just turning the roots into factors works fine when we have nice roots like -2, 8, -5, -4, integers that are roots. But if the roots that are given are a little bit unconventional, such as things involving I or things involving roots, we have a little trick method that can make this process a little bit easier. It's called the sum and product rule. What we're going to do is we're going to actually figure out how do you get that -5? How do you combine 8 and -3 to get -5? Well, if you added them and then changed the sign, you would get -5. 8 plus -3 is 5, and then change the sign. So, it's finding the sum and then switching the sign. How do you combine 8 and -3 to get -24? You just multiply them. This leads us to our sum and product rule. So when given the roots, you can build the polynomial equation they came from by adding the two roots to get their sum, multiplying them to get their product, and then using this equation, x squared minus the sum times x plus the product. The minus is accounting for our sign change that we need to do with their sum. So let's take a look. If we take the roots -2 and -10, the conventional method is just to turn those roots into factors, x plus 2 and x plus 10, and then multiply it out with FOIL, x squared plus 10x plus 2x plus 20 equals 0. For our final answer, x squared plus 12x plus 20 equals 0. If we do the new method, we want to find their sum and their product. So the sum of -2 and -10 is -12. Their product, -2 times -10, is positive 20. So when we use that equation, we get x squared minus -12x plus 20, or x squared plus 12x plus 20. For these problems, it's about the same amount of time to do the conventional method or the sum and product method, but as you're going to see, when we have roots and i's and things like that, the trick method is usually a little bit quicker. So let's go ahead and try some of these using that trick method. If the roots are root 10 and -10, first thing we want to find is their sum. Now, positive root 10 plus negative root 10 is going to cancel out, and their sum is just going to be 0. That's okay. For their product, root 10 times negative root 10 is going to be -10. The roots cancel out. So plugging that into our formula, x squared minus 0x plus -10 gives us x squared minus 10 equals 0. And you could probably check this one in your head, thinking about adding the 10 to both sides, square rooting. The roots you would end up getting are plus and minus root 10. Alright, let's take a look at number 6. Again, we're going to start by finding their sum. I find it helpful to stack these up, 4 plus root 5 and 4 minus root 5 when finding their sum. Be careful, just because they're conjugates does not mean their sum is 0. 4 plus 4 is 8. Positive root 5 plus negative root 5, though, does cancel out. For their product, we have to use FOIL. 4 plus root 5 times 4 minus root 5. Now, this is the time that because they're conjugates, the outside and the inside cancel out. Plus 4 root 5 and minus 4 root 5 goes away. And then last, root 5 times negative root 5 is minus 5. 16 minus 5 is 11. So using the formula here, we get x squared minus 8x plus 11 equals 0. Okay, for the next one, we'll go back to negative roots, so negative 7 and 4 are normal roots, but let's go ahead and use the trig method anyway. Their sum, negative 7 plus 4, is negative 3. Their product, negative 7 times 4, is negative 28. So our answer here is x squared minus negative 3 turns into plus 3x minus 28 equals 0. Alright, the last one here involves i's. So again, I find it helpful to go ahead and stack those together. Just because they're conjugates doesn't mean their sum is 0. 3 plus I and 3 minus I. The 3 plus 3 is 6. The i's go away. For their product, just like on the one above, we're going to have to use FOIL. 3 plus I times 3 minus I is 9. Plus 3i minus 3i goes away. Minus I squared. I squared is still negative 1, just like it was in the last chapter. So we're looking at 10 for their product. So our final answer here is x squared minus 6x plus 10 equals 0. Now, there's a little more to these roots with I than I'm letting on to you in number 8. We have something called the complex conjugate theorem. What this says is that complex roots always occur in pairs. So if a plus bi is a root, then a minus bi is also a root. You might have to add this in yourself. The big idea is that complex roots always occur in conjugate pairs. So even if in the problem I only list the root as 5 minus 2i, you need to know to automatically add in 5 plus 2i as another root. Now we're going to go about the problem just like we were the ones above. We're going to find their sum. 5 minus 2i and 5 plus 2i is going to add up to 10. And we're going to find their product using FOIL. So we get 25 minus 4i squared. Again, I squared is negative 1, so 25 plus 4 gives us 29. And our final answer is x squared minus 10x plus 29. Okay, lastly we have a fraction. Just a reminder, we don't want to have fractions as part of our answer. So while we could write 1/3, if we just do the factor method, x minus 1/3, when we FOIL that out, we're going to end up having fractions. So an easier way is to remember that x minus 1/3 is the same as writing 3x minus 1. So the trick that I usually tell my class is that you're going to put the denominator in front of x and the opposite sign of what's on top. So the 3 goes in front of the x, and then negative 1. Now it's just a FOIL question. So we've got 3x squared minus 15x minus x plus 5, which gives us 3x squared minus 16x plus 5 for the final answer. So again, just trying to remember, integral coefficients means no fractions. Alright, so that about sums it up for today. Now you know how to solve equations that go beyond quadratics with x cubes and x to the fourth, basically factor and then do quadratic formula or square root method, and you know if I give you roots how to work backwards and come up with the equation that would give you those answers when you solve.